So this temperature, in this class we just make it negative 273 Celsius, is referred to as absolute zero. Absolute zero is the temperature when the volume of an ideal gas becomes zero. And that is the smallest temperature possible. You cannot have less energy than zero energy. There is no such thing as negative Kelvin. 0 Kelvin is the end of the temperature scale. That it means zero energy, and you cannot have any less energy than zero energy. And so here we see you take the degrees Celsius plus 273 to get the Kelvin temperature, like we remember doing in previous chapters when we learned our temperature conversions. So 0 Celsius is 32 Fahrenheit is 273 Kelvin. For gases, you must always use Kelvin temperature. And Charles' law showed that the volume of a fixed quantity of gas is directly proportional to the Kelvin temperature. It's got to be the absolute temperature. That's important. You can only use Kelvin temperatures with gas laws. And the most common way to write this is the initial volume divided by the initial Kelvin temperature equals the final volume divided by the final Kelvin temperature. So 3 liters of hydrogen gas at negative 15 Celsius is allowed to warm to 27 degrees Celsius at constant pressure. What is the gas volume at 27 degrees Celsius? The important thing here is we need to convert temperatures into Kelvin. Negative 15 Celsius is 258 Kelvin. 27 Celsius is 300 Kelvin. And now we're solving for the final volume. So, step 1, we must cross multiply because we have something in the denominator. So we cross multiply to get rid of that. When we cross multiply, we get V1 T2 equals V2 T1. That's cross multiplying. And then to solve for V2, we divide both sides by T1. T1 divided by T1 is 1, giving us our equation. We plug and chug with the Kelvin temperatures. That's essential. You must use Kelvin temperatures to get an answer of 3.5 liters. Again, you must use Kelvin temperature with gas laws. The gas has a volume of 3 liters at 10 degrees Celsius. What is the temperature of the gas if it expands to 6 liters? Well, if the volume doubles, the temperature is going to double. But if you think that's 20 degrees Celsius, you're completely wrong because the Celsius scale is not proportional to energy. Therefore, we must convert to Kelvin temperature. And again, we are solving for the final temperature, T2. So we're going to cross multiply V1 T2 equals V2 T1 and then divide each side by V1 to isolate the variable. Then we add our numbers in and we get 566 Kelvin. And if we convert that back to Celsius, let's subtract 273. Let's take out a calculator and do that math. 566 minus 273, we get 293. So 293 Celsius is exactly twice the temperature of 10 Celsius. And again, that's why you can't use the Celsius scale, because it is not proportional to energy. So that's not intuitive in any way, shape, or form. You would never guess that. However, the Kelvin scale is proportional to energy. 566 Kelvin is twice the temperature of 283 Kelvin, because it is proportional to the energy that's there in the system. And therefore, all gas laws must use Kelvin temperature. At 321 Kelvin, a gas occupies 635 milliliters. If we decrease the temperature to 216 Kelvin, what's the new gas volume? Again, V1 over T1 equals V2 over T2. We're solving for the final volume. We cross multiply and divide each side by T1. and we get 427 milliliters. Avogadro's law. Equal volumes of different gases at constant temperature and pressure will contain the same number of molecules. So as long as the temperature and pressure is the same, 1 liter of hydrogen has exactly as many molecules as 1 liter of chlorine. It will have as many molecules as 1 liter of hydrogen chloride. And so the volumes are additive, and they're going to be stoichiometric because of that. You cannot apply this to solids or liquids because solids and liquids pack in many different ways, and so you can never be sure how many atoms or molecules you'll have in a given space. But gases all spread themselves out identically. And therefore, because the gases all spread themselves out identically, every standard unit of a gas will have the same number of molecules. 5 liters of hydrogen will have as many molecules as 5 liters of chlorine. The volumes are always equal. They'll have the same number of molecules. So if 12 liters of hydrogen react, and it's a 3-to-1 ratio, you know you need 4 liters of nitrogen for that reaction. So this is gas stoichiometry. Gas volumes are stoichiometric because they contain the same number of molecules, regardless of what gas it is, as long as the temperature and pressure are held constant. So given the following gas phase reaction, 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water. How many liters of oxygen are required to make 45.6 liters of water? Well, it's a 2-to-1 ratio. So we'll take our 45.6 liters of water times 1 liter of oxygen for every 2 liters of water, and we get 22.8 liters of oxygen required. And this only works because they're gases, and so gas volumes are stoichiometric. Molar volume. This is the volume that 1 mole of a gas occupies at STP. And STP is standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. 1 mole of any gas will occupy 22.4 liters at STP. All gases have this molar volume at STP because all gases spread themselves out the same. Therefore, the molar volume can be used as a conversion factor if the mass and volume of the gas are known. So 1 liter of oxygen at STP has the mass of 1.429 grams. So we know the density is 1.429 grams per liter. Show that the molar mass is 32 grams per mole. When we take the density times the molar volume, liters will cancel out, leaving us units of grams per mole. And so we'll see what the molar volume is. And so for oxygen, we see it is indeed 32 grams per mole, like you'd expect for O2, because each O2 has 2 atoms of oxygen, and each one weighs 16 grams per mole, so O2 is 32 grams per mole. If 3 liters of a gas measured at STP has a mass of 5.35 grams, calculate the molar mass. Again, density times molar volume. 5.35 grams divided by 3 liters times 22.4 liters per mole gives us 39.9 grams per mole. Again, this molar volume only counts at STP. So to use this shortcut of 1 mole being 22.4 liters, the gas must be at STP. If you're not at standard temperature and pressure, if it's not 0 Celsius and 1 atmosphere, then you cannot use that shortcut. Combined gas law. We saw Boyle's law. We saw Charles' law. There's also a third law, Amonton's law, where the initial pressure over the initial temperature equals final pressure over final temperature. And they took those 3 laws and combined them. So the P1 V1 equals P2 V2, plus V1 over T1 equals V2 over T2, and P1 over T1 equals P2 over T2, and then combine them all into the combined gas law. P1 V1 over T1 equals P2V2 over T2. And this now allows us to deal with 3 variables at once instead of only 2 variables at once. And again, STP is 0 degrees Celsius, which is the same thing as 273.15 Kelvin. And it's 1 atmosphere of pressure, which is the same thing as 760 torr or 760 millimeters of mercury.